In this video, I will be discussing about logistic regression. It's a supervised classification algorithm, mostly used for binary classification. It predicts the probability that an outcome belongs to a certain class. So consider one small example here. For this person, we are given a few informations like if this person is a smoker, what is the age of that person, if he or she has BP or cholesterol, and given this information, if we are trying to predict whether this person can have heart disease or not. So this is the type of binary classification we'll be doing using logistic regression here. So logistic regression can be used for many other classification problems like medical diagnosis, predicting whether a patient has a disease. That's an yes and no question based on symptoms, test results or genetic data. Example, predicting diabetes. Let's say 1 is someone has diabetes and 0 means he doesn't have, completely healthy. Credit scoring. So banks use logistic regression to predict whether a person will default on a loan. So based on the prior data, it will do the classification. Output 1 is default and 0 is no default, let's say. Marketing or customer behavior, predicting whether a customer will buy a product based on age, income and past purchases. Example, email click predictions, like whether someone will click on that product or not, that can be predicted based on few other parameters. Now, in this video, we'll discuss about this problem. Predicting heart disease based on age, blood pressure, cholesterol, whether someone is a smoker or not, and the output will be heart disease. So we'll have some training data set where for this inputs, age, blood pressure, cholesterol, smoker, will have this output given. This is the labeled output given. Consider we have this data set. We have n data rows x1, y1, x2, y2 till xn, yn, where xi's are the input and yi's are the output label. Xi is d-dimensional because we have age, blood pressure, cholesterol and smoker, these 4 attributes for input, right? So here in this case, input will be 4 dimension. So like for any xi, where I is from 1 to n, xi is xi1, xi2 till xid for d dimensions. So we have to come up with a machine or model where given any input x will predict the y, where x is any combination of the input, this age, blood pressure, cholesterol and smoker, and the output will be one of this 1 or 0 class, whether someone can have heart disease or not. Now, as this is a yes or no questions, the output is either 0 or 1. We need a Bernoulli distributions. And what is a Bernoulli distribution? A Bernoulli distribution is used when we have exactly 2 possible outcomes, success or failure. Let's say success is 1, failure is 0. Examples like flipping a coin. When we are flipping a coin, our output can be either head or tail, right? So let's say head means 1 and tail is 0. Email is spam or not, whether email is spam or not. So that also is a yes or no question. A customer buys or doesn't buy a product, that is also yes or no question, success or failure question. Disease present or absent. So all these are examples where Bernoulli distribution can be used. Now here probability of output class 1 is, let's say, probability of success. Let's say we are taking it as a small p. So probability always will be between 0 and 1. And probability of output class 0, that will be the probability of failure. And that will be 1 minus the small p. Now for any output class y, this formula holds. P raised to the power y times 1 minus p raised to the power 1 minus y. Now why this formula works? The formula works because y is only 0 or 1 here. And let's try to put the values here. If y equals to 1, the formula becomes what? P raised to the power 1 times 1 minus p raised to the power 1 minus 1, that is 0. So this is p. And if y equals to 0, it becomes p raised to the power 0 times 1 minus p raised to the power 1 minus 0, that is 1. So this is 1 minus p. So if y equals to 1, the probability is p. If y equals to 0, the probability is 1 minus p. So this is success, right? This is success and this is failure. And that's why this formula works for Bernoulli distribution. Now, from the data set we had, where we are having age, blood pressure, cholesterol, and smoker, in this data set, how do we predict the success or failure? So, this is our model, let's say. So, we earlier have discussed about linear regression, right? But in linear regression, our output was continuous, right? It was not a class variable, it was a continuous output. So, can we use that linear regression and try to modify the output to get a class value? We are trying to do that here in this logistic regression. What we will be doing? So, let's say using a linear regression model, we first predict some continuous value. Then transform that continuous value into probability P of success. This will be a value between 0 or 1. Now, if the value is between 0 and 0.5, then that will indicate failure or 0. And if the value is between 0.5 and 1, then that will indicate the success or 1. So this is the idea we are trying to apply for logistic regression. So in case of linear regression, our output was this. So we had this d-dimensional data and we were having this weights W0, W1 till WD, and f of xi for any input xi. This was the predicted output. W0 plus W1 xi1, W2 xi2 till WD xid. And if we represent it in vector term, we get W transpose xi. So this was the linear regression output. But this will give the continuous value, right? This will give some continuous value, but we want output as 0 or 1 here. So what we'll do, we will convert this continuous value into some value that is between 0 or 1. So P has to lie between 0 and 1 here. That's why we'll use sigmoid function. So we'll see now how sigmoid works here. So sigmoid function, will apply this sigmoid function on this output, W transpose xi. So this is basically probability P will be sigmoid of this W transpose xi. Now what is sigmoid function? Let's see quickly. So let's say there is a value A here. So A is some continuous value, right? So then sigmoid of this A will be 1 over 1 plus e raised to the power minus A. This is the formula for sigmoid function. We know that e raised to the power infinity it tends to infinity. E raised to the power minus infinity tends to 0, right? So let's put these things here. Sigmoid of minus infinity, what it will be? 1 over 1 plus e raised to the power infinity, right? Because we have raised to the power minus a here, so it will be e raised to the power infinity. So that is basically tends to 1 divided by infinity, and that tends to 0. So that means sigmoid of minus infinity is 0. You see the curve here? This is the sigmoid curve. So sigmoid of minus infinity will be 0. What is sigmoid of infinity? That will be 1 over 1 plus e raised to the power minus infinity. right? E raised to the power minus infinity is what? It tends to 0, right? So it will be 1 divided by 1. So it will be close to 1. So sigmoid of infinity will be 1, right? So sigmoid of minus infinity is 0, sigmoid of infinity is 1. So all the sigmoid values will lie between 0 and 1. Now let's see next what is sigmoid of 0. So this is the 0, and what is sigmoid value for 0? Sigmoid of 0 will be 1 divided by 1 plus e raised to the power 0. E raised to the power 0 is 1. So it is basically 1 by 2, that is 0.5. So when this a is 0, then sigmoid of a is 0.5. So half of this sigmoid thing is below 0.5, half after above 0.5. So 0.5 is the mean value for sigmoid. So that's why we can use sigmoid function to convert any continuous value to a value which is between 0 and 1. Now let's say for any input xi, output yi, our predicted output will be sigmoid of W transpose xi, right? So this sigmoid of W transpose xi, this is between 0 and 1, right? Because any sigmoid value will be between 0 and 1. We'll obtain 0 or 1 class using this thresholding during test time. So let's say if the sigmoid value is between 0 and 0.5, then that indicates 0, that is the 0 class, basically the failure class. If the sigmoid value is between 0.5 and 1, that indicates 1, or this is basically the success. So now probability of output class 1 is this sigmoid of W transpose xi, and probability of output class 0, that is basically 1 minus p, that is 1 minus sigmoid of W transpose xi. Now what is the likelihood? Likelihood is basically getting this output for a given input, right? So output, the likelihood will be sigmoid of W transpose xi when yi is 1. This is the actual output, right? So yi is 1, then this will be the probability, and 1 minus sigmoid of W transpose xi when yi is 0, 1 minus, like 1 minus p. So this we can represent with this formula, that formula we saw during Bernoulli distribution, right? So we are using the similar formula here. So the likelihood will be sigmoid of W transpose xi raised to the power yi times 1 minus sigmoid of W transpose xi raised to the power 1 minus yi. And let's see now again why this works. When yi is 0, then this likelihood is what? This one will be 0 and this one will be 1 minus 0, that is 1. So sigmoid of W transpose xi raised to the power 0 times 1 minus sigmoid of W transpose xi raised to the power 1 minus 0, that is 1. So this part only will get 1 minus sigmoid of W transpose xi. When yi equals to 1, we get this, right? Yi equals to 1 means this will be 1 and this will be 1 minus 1, so 0. So we'll just get this part, sigmoid of W transpose xi, that is the output for this. So when yi equals to 0, we are getting this 1 minus sigmoid of W transpose xi. When yi is 1, we get sigmoid of W transpose xi. So that's why this formula, this thing, likelihood formula, this works here. Now this is the likelihood we saw her here. Now we have to maximize the likelihood, right? So let's say we'll maximize the log likelihood, right? So let's take the log of this. So log of this will be what? Yi times log of this, log of sigmoid W transpose xi, plus 1 minus yi will get here, then log of this, right? So this is the log likelihood. We have to maximize this log likelihood. So instead of maximizing log likelihood, we can minimize the negative log likelihood, right? So we'll be minimizing the negative log likelihood. So we're just taking the negative here. Minus yi times log of sigmoid of W transpose xi minus 1 minus yi times log of 1 minus sigmoid of W transpose xi. So this is the loss function or the cost function for our problem, for our algorithm. And this is also called the binary cross entropy. So why it is called binary cross entropy? What is entropy? So for binary random variable, entropy is for any p, entropy of this will be minus p log p minus 1 minus p log 1 minus p. This defines the notion of randomness of a random variable. So our loss function that we want to minimize is this, right? Minus y1 times log of sigmoid of W transpose xi minus 1 minus yi times log of 1 minus sigmoid of W transpose xi. So it looks like, let's say this is P and this is Q, right? This Q sigmoid of W transpose xi, this is Q, right? So what we get? Minus P log of Q minus 1 minus P log of 1 minus Q. So this is similar to entropy, but we have P and Q is different here. Here we are getting minus P log P minus 1 minus P log 1 minus P. Here we just have two terms. So P and Q. So it looks similar to entropy, but P and Q comes from separate Bernoulli distribution. So that's why it is called binary cross entropy. Now this is the loss function we are getting, and we'll use this loss function in gradient descent. In our previous videos, in my linear regression videos and the gradient descent videos, I have talked about gradient descent on how we can use the loss function in the gradient descent update, the weight update. So Wt plus 1 will be Wt minus alpha of the gradient of the loss function. So for logistic regression, this is the loss function. We have to take the gradient of this loss function. Let's see that also now. How we will take the gradient of this loss function. So to take the gradient of this loss function, we also have to take the gradient of the sigmoids, right? So there is this sigmoid things and we don't know how to take the gradient of sigmoids. So first see how we calculate the derivative of sigmoid. So this is the sigmoid function. Sigmoid of A is 1 over 1 plus e raised to the power minus a. Now take the derivative of this sigmoid of A. The first derivative of sigmoid of A is, this is 1 plus e raised to the power minus a raised to the power minus 1. So our derivative will be minus 1 over 1 plus e raised to the power minus a square times derivative of this part 1 plus e raised to the power minus a, right? So that will be minus e raised to the power minus a. So this is basically this minus and minus you can cut. So you will get e raised to the power minus a divided by 1 plus e raised to the power minus a whole square. So you just divide this thing 1 over 1 plus e raised to the power minus a times e raised to the power minus a divided by 1 plus e raised to the power minus a. This is the what? This is what sigmoid of A, right? So we are getting sigmoid of A, and this is what? This is 1 minus sigmoid of A, right? So we are getting the derivative of any sigmoid of A will be sigmoid of A times 1 minus sigmoid of A. That's how we can calculate sigmoid of derivative of sigmoid. Now we got this sigmoid, derivative of sigmoid is sigmoid of A times 1 minus sigmoid of A. That we'll use while calculating the gradient of our loss function. So the loss function is this, we earlier saw. So this is for one ith term, right? One ith input. So if we are considering all the n samples, so it will be minus 1 by n times summation of I equals to 1 to n, this whole thing, yi thing, whole thing. So we have to calculate gradient of this loss function for gradient descent. That's what we are calculating here. This whole summation thing will come here and then take the gradient of this part. So why we are taking gradient with respect to the w, the weight, right? So yi will be here. The gradient of this log thing will be 1 over this sigmoid of w transpose xi. Then we have to take gradient of this sigma thing, right? So gradient of this sigma thing plus again we'll get 1 minus yi, then gradient of this log thing, that will be 1 minus sigmoid of w transpose xi, then gradient of this 1 minus sigmoid of w transpose xi. Now gradient of this sigmoid thing will get sigmoid of w transpose xi times 1 minus sigmoid of w transpose xi, and then gradient of this w transpose xi with respect to w, right? So then we'll get xi here. Plus again this part is remaining same. Then gradient of 1 minus sigmoid of w transpose xi. So get rid of this 1 and take this minus 1 out here. Minus 1 we got. Then we have to take the gradient of this sigmoid thing. So that will be sigmoid of w transpose xi times 1 minus sigmoid of w transpose xi. Then we have to take the gradient of w transpose xi as well with respect to w, right? Then we'll get the xi here. Now simplify this thing. So the same thing I have copied here. So let's see here. This sigmoid w transpose xi and sigmoid w transpose xi, we can cross this two. And here also we see 1 minus sigmoid of w transpose xi and 1 minus sigmoid of w transpose xi. This two also we can cross. We don't need that. So what is remaining? We are getting yi 1 minus sigmoid of w transpose xi, then xi, right? From here what we are getting? Y1, 1 minus yi, and we are getting 1 minus 1 here. So we are making it yi minus 1 times sigmoid of w transpose xi, then we are getting 1 xi. So this is the simplified version. Now again simplify this. We are getting yi xi minus yi sigmoid of w transpose xi times xi. From here what we are getting? Yi sigmoid of w transpose xi minus sigmoid of w transpose xi times xi. Now again this one and this one we can cut. These are same. So ultimately what we are getting? Yi times xi minus sigmoid of w transpose xi times xi, and this is basically a summation, right? So so now here we have one minus, and this minus we can reverse this. So this is our ultimately the gradient 1 by n summation of I from I equals to 1 to n sigmoid of w transpose xi minus yi times xi, right? So what is sigmoid of w transpose xi? Sigmoid of w transpose xi is basically the computed output, right? So we can write it as yi hat. So our thing, this is gradient is basically 1 by n summation of I equals to 1 to n yi hat minus yi whole thing times xi. So this is the computed output, this is the actual output. So that's how we are grading the gradient for loss function of logistic regression. Using this gradient, we have to use the gradient descent, and that's how we will optimize our problem.